Hello, and welcome to the Current Science and Technology podcast from the Museum of Science in Boston. I'm your host, Susan Heilman, and every week we bring you interviews with guest researchers and our museum staff covering science and technology in depth. Today we'll learn about the world's smallest motor. I have with me today physical chemist Dr. Charlie Sykes from Tufts University, who has created the world's smallest electric motor. Hi, Dr. Sykes.
Hello, Susan. How's it going?
It's going great. Thanks for joining me here today.
No problem.
So tell me about how small an electric motor is. I mean, I've seen, our cell phones have little teensy tiny electric motors in this. How small are we talking here?
We're actually talking just 1 nanometer in size, where a nanometer is 1/1000th of a meter, or to put it in comparative terms, about 100,000 times smaller than the width of a human hair.
Wow. Okay, that is pretty small. And what exactly is this made of? There's not many materials that are that small.
Yeah, we actually, because we're a chemistry group predominantly, we used a molecule which contains about 20 atoms. It's dioether. It's actually a molecule that is in some wines and gives things like brandies their flavor, but we liked it a lot because it has a sulfur atom in the center of the molecule that will bind pretty strongly to a metal surface, and then it has 2 arms that stretch away from that act as the sort of rotor arms as the molecule spins.
Okay, so it's a spinning motor.
Yep.
So how exactly does the motor work? Do you need to add electricity to it? What's the mechanical part of it?
Yes, it's an electrical motor. In order to actually see what we're working with, we needed a very special type of electron microscope called a scanning tunneling microscope. And that is a microscope that's not like an optical microscope that works with light. We actually use electricity or electrons, which are both particles and waves, to image what is on our surface. And with that microscope, we can see things as small as individual atoms and molecules. We were able to watch our motor spinning, but because we needed a way to power this tiny thing, we were actually able to use the electricity that we were using to image the molecule to actually power it at the same time.
Oh, wow, that's pretty cool. So you can't actually see a spinning motor, but you can tell from the microscope that it is spinning?
Yes. The way the microscope actually works is we have a very, very sharp metal needle, which would be like the sharpest needle in the world, that comes to a point that's so sharp there's just a few atoms at the very point of the needle, and that scans across our surface, and there's an electrical current that passes between that very sharp needle and what the sample is on the surface. And that records the image of what's on the surface, but then we can hover that needle over our motor as it spins, and every time the motor passes underneath that sharp needle, that electrical current will go up and down. So from that periodic beating of the electrical current, we could see both how fast the motor was spinning and also what direction it was spinning in.
So how fast does it spin?
It actually depends on both the temperature and how much electricity we deliver. So in our motor experiments where we're using electricity to spin the molecule, we wanted to actually go reasonably slowly so we could see exactly what was going on. So we typically spun the motor in the experiments at about 50 hertz, or about 50 rotational events per second.
And that's slow.
Yeah, that's, for us that's slow, because when we heat up the surface, we could get the molecule going well over 1 million times per second just by turning the temperature up.
Wow. Yeah, then I guess 50 times per second is slow compared to 1 million times per second.
Yeah.
So I didn't realize that there were other molecular motors, but other molecular motors are actually bigger than this?
Yes, there's 2 types of motors that scientists have synthesized. One is a group of motors called chemically powered motors. And those are, again, small molecules, but they sort of float around in solution in a beaker, and the scientists will say change the pH of the solution or maybe add chemicals to it and do sequential chemical reactions to spin the motor. And then there's another class that are driven by light, where you shine light on the motor and it flips into different orientations and spins. The issue with those 2 systems is that to study them, you're studying many, many millions or billions of molecules at the same time. one of the exciting things we found about making an electrically powered motor is we could excite one molecule at a time and we could watch just one molecule rotate in real time and really study its motion. And to sort of compare those classes of motors to naturally occurring ones, nature is way, way ahead of us right now.
It usually is.
Yeah. If you look at current technology that we have, with the exception of liquid crystals, we don't have anything in modern technology that relies upon the motion of molecules, where if you look in the body especially, your muscles move because of molecular motion. Cells can pump chemicals across the membrane in and out of your cells using chemical pumps.
Oh, yeah, that's true. Yeah.
Bacteria propel themselves around the body using tiny little molecular motors. And even kinesin can walk up and down tubules inside the body, dragging viruses along. So nature's showing that there's many different types of complex functionality you can do with molecular motors, but as technology, we're way, way behind, and we're just starting to show the first few examples of things that we can get some sort of directed motion from molecules.
So you mentioned that nature can already do it. Is that partly where you got your ideas from for this? Are you mimicking some motor that's in nature, or is it just the general idea?
A bit of both. Ours is very, very different to the motors in nature. Ours is much, much smaller molecule, much simpler molecule that we can sort of study and understand. But some of the inspiration from nature comes because when you really think about how these machines in nature work, the amount of power they have available to them is really tiny compared to the amount of random sort of thermal buffeting they get inside the body. Because they're in solution, they're getting constantly hit by water molecules and other things. The amount of energy is just a few percent of the random thermal noise they're experiencing. So they operate in a very, very different regime to classical motors that we have in our cars. People like Dean Asterman, theorists from the University of Maine, have shown many nice studies where the thought is that instead of using the tiny amount of power that they have available to them, biological motors won't just push against the forces that are hitting them. They'll actually use their power to sort of hang on, and then when the wind is blowing in the right direction, they'll let go. So it's a very, very different way of operating than a car or an electric motor, which just pushes against friction.
Right, right. That makes sense. That's wow. It's amazing how clever biology is.
Yeah. So when we looked at how our motor was working, it's somewhat analogous because our motor is not turning at the same speed in the same direction the whole time. It's actually sort of jittering around on the surface. If we only watched it for a few turns, you'd almost think it was behaving randomly. It's only when you watch it for long enough you see that it's actually turning more in one direction than the other. So it looks a bit more like the biological systems that they sort of look like they're behaving randomly until you watch them long enough, then you can see what they're doing. The same way with us, we could only show up to like 5% preference for, say, a clockwise rotation versus anti-clockwise, so it was still kind of jittery at that point.
You said at that point, so is it now less jittery and more spinning, or?
No, that's right now. That's the best we can do is to go
Okay.
5% more in one direction than the other. But in a way, if you're spinning 1,000,000 times per second, that's still a lot of net rotations in one direction.
Sure, that makes sense actually. Yeah, when you put it that way. So nature's already got it down. We talked about how biology already uses these molecular motors. What do you think your molecular motors might be useful for?
Yeah, to be quite honest, the actual applications are fairly distant. You know, you're talking 30, 50 years. But one of the things we would think of is because we have this tiny molecule that is rotating, if we attached charges to that, so had one end of the motor be positive and the other end be negative, as that thing spins, it should emit light, like, for example, microwaves. So you could have a tiny microwave generator, just 1 nanometer in size, or vice versa. If you hit the thing with radio waves or microwaves, you potentially make the molecule spin. So you'd have a novel way to move from an optical signal to a molecular mechanical signal, then to an electrical signal. So you might be able to make a new class of optoelectronic devices which interface between electricity and light at the nanoscale, and also move those in very fast sequence.
So it sounds like there are potentially a lot of applications, but none that are, right down the road.
Yes, it's still tricky to set up and monitor these systems. To put it in perspective, the temperatures we had to go to really study what was happening in our motor system was about minus 265 Celsius, I believe.
Yeah.
So we had to go to very low temperatures to get everything to stop moving to the extent that we could actually see what was going on.
What do you plan on doing next in the next couple years, not the next 30 to 50 years?
Yeah, so I think the next big step for us is to say, well, can we get work out of the motor? Can we put a rotor next to that and spin the motor and actually watch the mechanical rotation propagate to the next molecule and the next? So it would be analogous to making a really small set of gears or cogwheels,
Right. Mm-hmm.
tiny gearbox, to see really if mechanical energy transfers in a similar way to what we'd expect in our everyday labs, or if it's very, very different on the nanoscale.
Well, this sounds incredibly novel, and once again, another example of technology trying to mimic what nature has already been able to accomplish. So you claim smallest electric motor. Is this a Guinness Book of World Records thing you can do here?
Yes, it is. We applied for the record almost a month ago, and actually just received the official certificate. I have it here on my desk. It arrived in the post yesterday, so we are now world record holders for the world's smallest electric motor.
Very cool. Well, congratulations on that, and thank you for speaking with me today.
No, it's my pleasure. Thank you very much.
That's it for this week's show, but be sure to come back next time for more of the latest in science and technology. This podcast is a production of Current Science and Technology at the Museum of Science in Boston, part of the Boston community for over 175 years. For more information, visit our website at www.mos.org/CST or email us at podcast@mos.org. Thanks for listening.